Hi, my name is Alex. I am a senior mathematics major with a concentration in actuarial science with minors in business administration and theater and music. After graduation, I plan on working in a finance slash accounting position in a small business or firm. I would like to continue my studies as well at the Mount for another at least 2 years in an accounting program with the MBA certification as well. This research experience has allowed me to study the two things I'm passionate about, mathematics and music. So I'd like to thank the honors program for allowing me to take part in this study for this semester. And here is the mathematics behind music. So math is the study of numbers and its patterns, and it's used basically everywhere, from the generally accepted accounting principles, in the classrooms, and the stock market. But math can also be found in other hidden places as well. Many people hear this treacherous word math and they look the other way because they don't want to be associated with it. But many people also don't know that they're using math in their daily lives. Mathematics could be found when purchasing a cup of coffee, found in nature, and for the concentration of my studies, music as well. In my studies this past semester, I've compared frequencies of notes to the period of vibrations to see how chords are formed, explored how sequences play a role in nature, and how musicians use Fibonacci sequences in their works of art. I also attempted to write music from a mathematical standpoint. So let's start with wavelengths. Wavelengths are used commonly in physics to determine the period of frequency. In music, we can also measure wavelengths of notes to see how long the note produced takes to complete one wavelength. The more frequencies per note, the higher the pitch, and inversely, the wavelength will decrease in length. So to continue with wavelengths, the graph below shows three different sine curves that mimic how wavelengths in different notes on the piano react. So the red will equal B8 on the piano, blue would equal B7, and green would equal B6. So as you can see, the wavelengths have different amplitudes, but that doesn't really matter. It just shows for more graphic representation. Each wavelength is different. So in order for a sine curve to be completed, it has to cross through the x-axis twice. So following it up and down and back up, we see that the red, or B8, curve stops at around 4.37. 4.37 is the amount of centimeters of wavelength of B8. Next, the blue line represents B7. We follow it up, down, back up. It's about 8.7. So that is double of the 4.73 centimeters. And each time you go an octave down, the wavelength will increase doubly. Same goes for green. Since the blue is 8.7, we follow all the way to green, and it's about 17.4. So there we go. It takes 4 B8s and 2 B7s to be 1 B6. Wavelengths and frequencies have an inverse relationship. As frequency increases, the length of the wavelength decreases. This occurs naturally because in order to complete X wavelengths in Y time, the beat would need to occur more frequent. And I made this graph, a visual representation between frequency, which is represented in blue, and wavelength in centimeters represented in green. And as frequency grows, our wavelength will decrease. So let's start with Fibonacci sequences. The Fibonacci sequence is amongst the most well-known mathematical patterns for its applications in various events such as mathematics, nature, and music. So the set of numbers was discovered by Leonardo Fibonacci Pisano. He was a mathematician known for many publications in the 13th century, one of which was the Liberace. It introduced Europe to the Indo-Arabic numbers. During his studies, Fibonacci asked the question, how many pairs of rabbits will be born in a year? Starting from a single pair, if each month each pair gives birth to a new pair, which becomes reproductive from the second month. This led to what we know today as the Fibonacci sequence. If we start with 0 pairs of rabbits and introduce a pair of infertile rabbits to an environment after 1 month, we then have 1 pair of rabbits. After 1 month, that pair of rabbits becomes fertile and produces another pair of rabbits, leaving us with 2 pairs of rabbits. After another month, the chain continues until there are 3 pairs. Then another month, 5 pairs, 8 pairs, and so on. So here's a representation of Fibonacci numbers. So if we look at f of n minus 1, the second column from left, we see the Fibonacci sequence. So it goes from 1, 2, 3, 5, 8, and so on. To get these numbers, it's the sum of the previous 2 terms. So 0 plus 1 is 1, as you can see following the chart. 1 plus 1 is 2. 2 plus its preceding term 1 is 3. 2 plus 3 is 5, and so on. We can also make different relationships out of these numbers. So if we divide f of n minus 1 divided by f of n minus 2, we get closer to the golden ratio. And I'll explain that more as we continue with the presentation. Lastly, another relationship that you can do is doing f of n squared and addition of the preceding terms. So let's start out with our 5th row down. So 1 plus 1 plus 4 plus 9 equals 15. Where do we get those numbers? The sum of the preceding terms. 1 squared plus 1 squared plus 2 squared plus 3 squared. That equals 15. And it's also equal to 3 times 5. What's really cool about that is that 3 and 5 are both Fibonacci numbers. Let's do this again for the row starting with 5 at the leftmost. We want to get to 273. That's 1 squared plus 2 squared plus 1 squared plus 3 squared plus 5 squared plus 8 squared plus 13 squared. And that gets us to 273. And what's cool about that again is that 21 times 13 is equal to 273, and 21 and 13 are both Fibonacci numbers. So Fibonacci numbers in nature. Many mathematicians began to apply Fibonacci sequence to everyday things, and as new realizations were made, many of which were found in nature. Mathematicians observed flowers and other species of plants and formed relationships on the amount of petals or seeds in a plant. For example, Parnassians have 5 petals and daisies have 13, both of which are Fibonacci numbers. We can also see this as the numbers of seeds represented in sunflowers on a curve. These represent Fibonacci numbers, and the list goes on and on. The golden ratio. The golden ratio, also known as phi, is equivalent to approximately 1.6180. It's a mathematical concept that describes the Fibonacci numbers through perfect proportion. It exists when a line is divided into 2 parts, and the longer part A divided by the smaller part B is equal to the sum of A plus B divided by A, which both should equal 1.618. So if we look at the top right in that diagram, that rectangle, and we say that A is 13 and its preceding term Fibonacci term would be 8, those are both Fibonacci numbers that are consecutive. We get 13 divided by 8 would equal 1.625, which is pretty close to the golden ratio. Now, if we add those two, 13 plus 8 is 21, and divide it by its largest root, which is 13, we get a number even closer to the golden ratio at 1.61538. So the golden ratio is very cool, and as you can see, it could be in different patterns as well, most known for its shell-like structure. It can be seen in weather patterns and many snail shells. Fibonacci patterns are found in music from Mozart to even recent musicians such as Lady Gaga. In his works, Mozart used the formula for the golden ratio to make his exposition and recapitulation divide into the golden ratio. For example, the first movement of Mozart's Piano Sonata No. 1 in C major is composed of 100 measures of music, 38 of which are an exposition, and the remaining 62 are a recapitulation. If we divide 62 by 38, we get 1.6316, but it doesn't stop there. 100 divided by 62 is even closer to that golden ratio, totaling in at 1.6129. Lady Gaga did this in one of her recent songs as well. Her key change in Perfect Illusion is precisely timed at 111 seconds of the song. Now, when we multiply the time of the key change, 111 seconds, times by 1.618, we get 179, and that's the exact length of the song. We notice these patterns on multiple occasions, which is very cool to see how mathematics could have a role in music. We see that the golden ratio is also in the Stradivarius. The Stradivarius is believed to be the most perfect violin in all existence. It was created by Antonio Stradivari. The instrument makes beautiful and sonorous sounds. Each component of the violin was carefully structured to oblige by the golden ratio, as shown in the diagram in the right corner. Musicians took the golden ratio into consideration when making their music, but the golden ratio represents beauty, and every musician wants to capture its essence in their work that they produce. Expanding more on Fibonacci numbers, we can see this pattern being used by Bela Bartok's third movement in his opening xylophone solo. The solo begins with one note, followed by increasingly faster notes in a pattern of a Fibonacci sequence. Using this was an innovation to his works. Bartok kept his work semi-private to other musicians because he wanted to keep his breakthrough to himself, and no other musician in his time would catch up to his findings. Just like Mozart and Lady Gaga, Bartok also incorporates the golden ratio into his works. Unlike Lady Gaga, who probably didn't have a calculator by her side while writing her music, Bartok carefully measured mathematics into his compositions. Transformational theory, developed by David Lewis, focuses on the relations of music rather than the objectives of it. To further explain, chords are transformed from one to another. Transformational theory focuses on the movement of notes in intervals. We can also use analytics to predict patterns and make chords in math using a variety of formulas. The most math-based music is applying timing to rhythmic patterns to achieve soothing and appealing patterns to the ears, and the most skilled musicians can acquire that skill. The picture to the right depicts math being an integral role in the production of music. However, most people don't think of math when music is being played. But returning to the point made, it's in the timing, as well as places like how long a note should last, where to take a breath when singing, and the key that's being used. Math is ultimately the underlying foundation of music. So writing a song mathematically. Firstly, we want to analyze ways to incorporate mathematical values into the song, such as Fibonacci sequences, golden ratio, and note lengths. I chose to concentrate in the golden ratio. But first, I started to analyze Fibonacci numbers and their relationships in terms of remainders. So an octave contains 7 notes for each number. I chose the mod 7 process. Based on my discoveries, I organized the numbers to match notes and started to create rhythms. Lastly, I created Public Speaking, which is a song about developing the courage to talk in public. The singer realizes that with a little help, he can talk in front of people. Using the golden ratio, he picks up that sense at 94 seconds out of the total 152 seconds of the song. So 94, the bigger part, and the smaller part is 58. When we divide that, we get 1.6207, which falls in the range of the golden ratio numbers. But what's really cool is that 152 divided by 94, the whole length of the song divided by the bigger part, is 1.6170, which is significantly closer to that golden ratio number of 1.618. Lucas numbers contain similar principles to the Fibonacci sequence. However, we start with a different term. This number would be 2 instead of 0 or 1. And we take the preceding terms, the sum of them. So the list goes something like this: 2, 1, 3, 4, 7. Again, we're adding the preceding term. So 4 plus 7 is 11. 7 plus 11 is 18. 29, 47, 76, and the numbers continue in an increasing pattern. These numbers also signify the structure of the golden ratio as represented in the structure below, creating that shell-like structure. So using mathematical concepts in this experiment, I used both Fibonacci sequences as well as the Lucas numbers. So again, they simulate the Fibonacci sequence numbers, but they have a different starting point. So as you can see, I listed the Fibonacci sequence numbers and the Lucas numbers. I did module 7 because an octave has 7 notes. So 0 mod 7 is 0, 1 mod 7 is 1, 1 mod 7 again is 1, 2 mod 7 is 2, and so on until we get to a number greater than 7. 13 mod 7 is 6. So 13 has one whole part of 7 and a remainder of 6. So that means the remainder is 6. 21 divides into 7 perfectly. So there is not a remainder in this. And then I added the notes to it. As you can see, 1 is F, 2 is G, 3 is A, and so on. So for our first number, 0, 0 would be E. I did the same thing for the Lucas numbers with the same module, R mod 7, and I got these notes as well. So using the remainder theorem, I took the remainder of each number and assigned it a note. In this case, I used F major as each note. So for each note, remainder, 1 would equal F, 2 would equal G, 3 would equal A, and so on. Using the Fibonacci sequences, I arranged the notes into quarter notes, and this is what I got. After listening to it a couple times, I transposed it into a different rhythm, and this is what I got using that rhythm. I tried other ways, including inversely transcribing our notes, but nothing really worked, so I moved on to Lucas numbers. And this is what I got for quarter notes for Lucas numbers using the remainders. And then I added a rhythm to it. And then something cool happened. So I attached the inverse of the notes into the regular notes. So starting from the last to the first, tied in with the first to the last. And it created this. And I also added a little bit extra to it just to make it sound a little bit better. This is what I got. Here's the song Public Speaking, and the sheet music goes along with it. So the process began in the fall semester of 2019 when I did this in honors by contract with Dr. Entrican. The goal was to write a song and nothing more to it in mathematical concepts. However, when I started the mathematical part of it, I decided to emulate the golden ratio into it and see if I could obtain a perfect spiral in it. So the song length is 152 seconds long, and the point of the song is to have someone realize that they can speak in public. People or myself sometimes always don't speak up. So writing in this perspective of a person who is shy and somewhat finding that he can speak his mind. Has this revelation at around 94 seconds, and then the remaining part is 58 seconds of that 152. 94 divided by 58 gets us really close to that golden ratio, and 152 divided by 94 gets us really, really close to that golden ratio. So definitely incorporating that into the song was definitely really cool from a mathematical standpoint. With this song, I also added lyrics, so I'm going to play you the song, and I hope you like it. This is the song Public Speaking. So, people that know me know that I can't talk well in front of people. Knows that I cannot talk when there's somebody there. I can't talk to myself. I can't look when I stare. Well, here's the thing. Nobody cares. I don't know how to talk to people or talk when people are around. They say I swallow my own words. Isn't it absurd? I guess I don't know. Knows that I cannot speak when somebody's around. I can't get my words out. I don't produce a sound. But here's the thing. It won't be found. I look and search and that's more important. But nothing wants to come out. They say it's just a big fear. I can talk, oh dear. I can. No, I can't. Yes, I can. Well, not in front of people. Don't know how to do it. I really want to learn, but I can't even get a word out. I don't know where else to turn, what to do, what to say. I really want to speak out my mind. Who's starting here today? I'll try to be more confident in the words I say. Oh, in the words I say. I want to learn, I really do, and all I need is some practice from you. And I think I can. No, I know I can. Talk in front of people. I can do it. Public speaking. In front of people. I can. So, a little conclusion. Math can be found in our everyday lives, from nature to making a purchase at the grocery store. However, math can be found in much more than that. In my research, I found a new connection between theories used in mathematics, and they're really fascinating to discover. There's so much more to math and music that they have in common, but seeing the connections between wavelength and chords, Fibonacci sequences, and the golden ratio, even in past music and current music as well, was very fun to research, and it was a great learning opportunity. And here are my works cited, and that finishes the presentation of the mathematics behind music.